Hello everyone, welcome to chapter 7 Atoms and Spectra. Up until now, we have mostly been looking at the universe with our eyes or through telescopes. So, we learn how telescopes collect light, how cameras capture images, and how spectrographs spread light into spectra. And now, we are taking a big step forward. Instead of just seeing the universe, we are going to start understanding what that light actually tells us. Think of light as a messenger. It carries secrets about stars, planets, and gas clouds that are far beyond our reach. So, by the end of this chapter, you will start to answer questions like how do atoms interact with light? What types of spectra can we observe? And what can these spectra tell us about the objects in space? So, get ready to become a cosmic detective and read the clues hidden in starlight. Now, let's look at what you will be able to do by the end of this chapter. First, we will explore how atoms interact with light to produce a spectra. So, this is the foundation. Without understanding this, we can't interpret any of the colors or lines we see in spectra. So, we will see how electrons in atoms absorb and emit light in very specific ways. And next, we will identify the different types of spectra we can observe. Some spectra are continuous, some have dark absorption lines, and others show bright emission lines. So, you will learn how to recognize them and what they mean. Finally, we will learn what these spectra reveal about celestial objects. So, from them, we can figure out the chemical compositions of stars, measure motions of gas, and even uncover physical conditions in distant nebula. So, as we move through this chapter, keep these objectives in mind. They are your guide spots for what to focus on. So, think of them as your roadmap to read in the universe's hidden messages. So, here's the roadmap of what we will cover in this chapter. We will start with the atoms, the building blocks of everything in the universe. So, understanding their structure is key because the way atoms interact with light is what creates the spectral lines we observe. Next, we will look at the interactions of light and matter. So, here we will explore how electrons absorb and emit light and how those interactions leave distinct fingerprints in spectra. So, finally, we will move to understanding spectra. So, this is where we tie everything together, learning how to interpret the different types of spectra and how astronomers use them to uncover the chemical composition and motion of celestial objects. So, think of this chapter as a toolkit for reading the universe. Each section builds on the previous one, so by the end, you will be able to decode starlight and other cosmic messages. Alright, let's zoom in from stars to the tiniest pieces that make them up, atoms. So, I'm going to walk you through what an atom really looks like and why most of it is actually empty space. Now, first look here at the diagram. The little dot in the center is the nucleus. That's where almost all the mass lives. The fuzz around it is the electron cloud. So, visually, this picture helps us accept that an atom is not a solid billiard ball but a tiny nucleus with a large region around it where electrons hang out. Now, atoms contain a nucleus with protons and neutrons. So, at the very center of every atom sits the nucleus. So, think of the nucleus as a tightly packed core. Protons are positively charged, neutrons have no charge. So, together they make the mass of the atom, and the number of protons is the atom's identity. So, you change that, you have a different element. 6 protons, that's carbon, and 7 protons, that's nitrogen. So the number of nitrogen is the atom's identity. And next, electrons are extremely light and negatively charged. They are not sitting still like little marbles, but more like a cloud where they are most likely to be found. Normally, the number of electrons matches the number of protons. So the charges balance out positive to negative. Remember, protons are positive and electrons are negatively charged. And that balance makes a neutral atom. Now here's the shocking part. Matter is not really solid. First, let's take an example. A hydrogen atom. Now a hydrogen nucleus is about 1.7 times 10 to the power minus 15 meters across. So the electron cloud extends to about 2.4 times 10 to the power minus 10 meters. So if you scale both up by a trillion, that means 10 to the power 12, to make them easier to picture, then the nucleus becomes 1.7 millimeters, about an apple seed. And the electron clouds becomes 240 meters across, a couple of football fields. So what does that mean? That means most of the atom's volume is the space between nucleus and electrons. And that's why matter is mostly empty at the microscopic scale, even though it feels solid macroscopically. Now, why we use scaled models? Models are practical tools. They are not literally true in every way, but they let us reason. Now, saying the nucleus is an apple seed and the electron cloud a stadium helps us appreciate distances and forces, even though the atom behaves quantum mechanically. Alright, now that you can picture an atom's structure and scale, let's look at how atoms can differ from one another. Different elements, isotopes and ions, because those differences matter when we read spectra. Again, here's the magnifying hydrogen example we said earlier. So magnifying a hydrogen atom by a factor of 10 to the power 12 makes the nuclear size of a small apple seed and the surrounding electron cloud about the size of a stadium. Can you imagine? Now, there are three ways atoms vary: by protons, neutrons and by electrons. So each change has real observational consequences. First, the count of protons in the nucleus is what we call as the atomic number. And that number defines the chemical element. It's more like the element's ID number. For example, carbon always has 6 protons, and change that number and you have a new element altogether. 7 protons, that's nitrogen. So changing a proton change the element itself. Now why this matters? The nuclear charge or the number of protons sets how strongly electrons are attracted, and therefore it affects the atom's available electron energy levels. And that affects the light the atom can absorb or emit. And next, atoms of the same element can have different number of neutrons. Carbon 12 has 6 neutrons, while carbon 13 has 7 neutrons. But both are carbon. One is just little heavier. So neutrons change mass, not the charge. And these atoms with the same proton count but different neutron counts are called isotopes. So chemically, they are almost identical because chemistry depends primarily on electrons. But isotopes can affect properties like atomic mass and tiny spectral shift. And these isotopes can be especially important in astronomy for subtle diagnostics. For example, isotope ratios can tell us about nuclear processes or origins of materials. And next, electrons. They are loosely held compared to protons and neutrons. So if an atom loses one, it becomes positively charged. And if it gains one, then it becomes negatively charged. That means ions form when electrons are removed or added. Therefore, ionization changes the atom's net electric charge and its electron energy pattern, meaning the wavelengths it absorbs or emit also change. And in hot stellar atmospheres, many atoms are ionized. So when we look at a star's spectrum, we might see lines from neutral atoms and from ions. And each tells us about temperature and conditions. We will learn them later. Now, when atoms share or exchange electrons, they form molecules. That means atoms bond by sharing or transferring electrons to make molecules. And in every hot star, the violent collisions break molecules apart. But in cooler stars or gas clouds, molecules survive and leave distinct signatures in spectra. So, for example, molecules like titanium oxide are clues to low stellar temperatures. Alright, now we have seen how atoms can vary. So, let's zoom into the electrons themselves, because the allowed electron energies are what produce the spectral fingerprints we read. Okay, time for the quantum idea, which means electrons don't roam freely. They live in permitted energy levels. So understanding these levels is essential to connect atoms to spectral lines. Now can you see the image? These three sketches show how different elements have different patterns of permitted orbits. So notice how hydrogen's pattern is simple while boron is more complicated, and that complexity shows up in more complicated spectra. Now electrons are bound by the Coulomb force, and that's just the attraction between negative electrons and the positive nucleus. So the closer an electron is, the harder it is to remove, and we call that binding energy. So that means an electron near the nucleus is tightly bound and needs a lot of energy to escape, which means larger binding energy. But an electron farther out is more weakly bound. That means smaller binding energy. Now ionization energy is the energy required to remove an electron completely from the atom. So if a proton supplies at least that much energy, then the atom can be ionized. And once ionized, its permitted energy pattern changes significantly, which changes the atom's spectral signature. Alright, now think of each allowed orbit as a shelf in a bookcase. You can put a book on shelf 1 or shelf 2, but you can't put it between shelves. That means electrons can only occupy those permitted energy levels. So we say that atoms obey quantum mechanics, which means only certain discrete energy states exist, and each element's nuclear charge creates its unique set of permitted levels. So the pattern of permitted jumps between levels is unique for that specific element, and that's a quantum rule. Now if an electron drops to a lower level, then it gives off energy as light. But if it jumps up, then it absorbs light. Now because only certain energy differences are possible, therefore atoms absorb or emit photons only at specific wavelengths. And that's why spectral lines are narrow and characteristic. And there's also a rule that's saying no more than 2 electrons can occupy the same permitted orbit, which we call as the Pauli exclusion principle. So that rule explains why atoms stack up their electrons in layers, shaping chemistry and spectra. Now imagine an electron falling from a high orbit to a low one. So what happens to the energy difference? It escapes as a photon, a particle of light, and that photon's color depends on the size of the jump. So this is exactly what creates the sharp lines we see in spectra. Now with the quantized orbit in mind, let's ready to put atoms into the astronomical context. How their jumps and states appear in real spectra from nebula, stars and phenomena like aurora. So let's bring everything together and see how atoms leave their marks in the light we receive from space. Now when electrons jump between energy levels, they absorb or emit photons at specific wavelengths. And the result is a pattern of lines in a spectrum. And that pattern is unique to each element. Just like a fingerprint, no two elements have the same set of lines. So in emission, you see bright lines where light is produced, and in absorption, you see dark lines where light at particular wavelengths is removed from a continuous background. Now this picture of the aurora is a vivid example. The green glow comes from oxygen atoms, while the red glow is linked to nitrogen atoms. So those colors are direct evidence of atoms emitting light at their characteristic wavelengths. So when we look at the sky, we are literally seeing atomic fingerprints painted across it. So back in the early 1800s, Joseph Fraunhofer studied sunlight with a prism and noticed dark lines crossing the spectrum. But at the time, no one knew what they were. And decades later, scientists realized those dark lines matched elements on Earth. So this was a breakthrough that showed the sun and by extension the stars contain the very same elements we find here on our planet. So by studying these spectral lines, astronomers can determine the composition of a star or gas clouds, which atoms, ions or even molecules are present. And they can also estimate temperature because ionization states and molecular features depend on how hot the gas is. And finally, they can measure motion. So if the lines are shifted towards the red or blue, it means the object is moving away or towards us. And we can calculate its speed using the effect called Doppler effect. So in short, spectra are the ultimate detective tool. They reveal what something in space is made of, how hot it is, and whether it's coming closer or moving away. And that's a lot of information, all from light. So let me leave you with a thought. Almost everything we know about the stars, their chemistry, their temperature, their movement, comes from these lines of light. And without them, we would almost blind to the universe. Alright, with this, we conclude section 1 of chapter 7. Now here's a quick recap. Atoms are mostly empty space with a tiny nucleus made of protons and neutrons and a cloud of electrons around it. And protons set the identity of the element. Neutron gives us isotopes. And electrons can be gained or lost to form ions. And atoms can also bond to make molecules, especially in cooler environments. And most importantly, electrons live in specific energy levels. And when they jump between those levels, they absorb or emit light at very specific wavelengths. And these unique light signatures act like fingerprints, allowing astronomers to figure out what stars, nebula, and planets are made of. Alright, now in section 2, we will dive into how light and matter interact to produce those spectra, the key to decoding the universe's messages.